All right, and let's share screen. So for this problem, your best choice to let u is to be everything in the denominator. The derivative of that, or differential, you would just bring a 3 down in front of the exponential. And a thing I saw some people miss this guy. He has to be there. So if you look at the problem itself, we have most of that up here. We're just missing the 3. So you need to introduce a 3 here and counteract it on the outside with the 1/3. So this becomes 1/3 integral. Everything on top is du and everything on the bottom is u. The derivative, or sorry, the integral of du over u is a natural log. And technically, you should have absolute value for that. And then the last thing you have to remember, plus c. So any questions about that guy before we continue with integration by parts?
No, that makes sense to me.
Okay. All right, so I'm going to do 1 or 2 integration by parts problems, and then I think I'm going to take maybe 15 minutes to let you guys try some and break you off into groups. So we did problem 1 and 2 yesterday. Actually, I think, let's see. I will leave this one for you guys to try. So I will start here. And let me make sure I'm sharing the document so you know what I'm talking about. There we go. All right. So I left off at this problem here. I think I'm going to let you guys try this one. The only difference in that problem versus A or B that we did yesterday is that notice there are no bounds on this problem, but on C there are. So when evaluated, you have to apply those bounds at each part. Let me see if actually any of these have bounds. Okay, so at least I can demonstrate that for you. Okay. So these ones here say that they're not apparent, as in you look at it and we're for by parts, we are kind of trained to say, okay, we need 2 functions. But if you look at this integral, there's only a single function here, right? It's natural log x dx. So that's why it says it's not apparent to be done by parts, but you still can use it. And notice it says perhaps assign dv to just be dx. So I'm going to let u equal the natural log, and dv is just dx. Then it's my task to calculate du and v. Du is the derivative of the natural log, which is 1 over x. And of course, we need our dx. And the integral of dv is what gives us back v. Well, the integral of a differential dx is just x. So then if we follow the pattern, we need u times v minus v times d, or the integral of v du. Now, when we do u times v, that's a multiplication, which means it can be u times v or v times u. Right, I can write it in either order, and I'm going to do that here because I want the x to be in front of the natural log. It's multiplication, so you can commute. Then I need minus the integral of v times du. So x times 1 over x dx. And that's going to turn out to be really nice for us because x times 1 over x cancels. And it's just the integral of dx, which we should all know, as we just did it above, is x, and of course we need a plus c. You could also see this written as x times the quantity, natural log x minus 1, plus a constant. Either one of these is acceptable. For the second one here, we are given arc cosine, and this one has bounds. So again, there are no two functions. There's just one function, right? And so it might not be something that you look at and say, okay, this is definitely by parts, but we can still use the technique if we let dv equal dx. So I'm going to let u equal the arc cosine. And if that sounds weird, arc cosine is the same thing as inverse cosine, or cosine to the minus 1. That's just really bad notation. And then, of course, we've got dv equals dx. So calculate du and v. So the question is, what's the derivative of arc cosine? Anybody recall that one?
Wouldn't it be the inverse of negative sine? So in this case, like arc sine by chance?
I don't think so. No.
Okay.
Is it 1 over root 1 minus x squared?
I believe off the top of my head it's minus, but I'll check that really quick. So I was trying to go back to the first notes that I gave you. Remember, there was a chart there for integrals.
Yeah, but I don't think you have the arc cosine on there. Just arctan and arcsine.
There's arcsine and arctan. So arc cosine, yeah, has the minus sign in it, I believe. But I will triple check myself here. Yep, that's good. All right. So again, that's not one that I expect you to recall necessarily off the top of your head. I could never memorize those for some reason, so don't expect you guys to do that. You don't use arc trig functions that often anyway. All right, so we've got all of our pieces here. We just need to write it out. So the answer is now going to be u times v minus the integral of vu, or v du. Again, I'm going to put v first, just because I like to call this math etiquette. It's kind of the right way to, or the correct way to write things. Right? You wouldn't necessarily write arc cosine of x times x. If you do, sometimes it can be confusing. You may think that the x on the outside can be combined on the inside, and that is not the case. So I'm going to put it in front here. This also has to be evaluated from 0 to 1. Minus the integral of v times du so that would look like that. Again, from 0 to 1. These two minus signs here can be combined and make this plus. And rather than evaluate the first piece, I'm just going to bring it along for the ride. And I'm going to integrate the second piece and then evaluate everything from 0 to 1. So how do I solve that integral? Any ideas?
U sub?
So that is a u substitution. So let's actually use a different variable since we've already used u and v. Anyone have a problem with me using w?
No.
Okay, so I'm going to let w equal everything under the radical. The differential is then minus 2x dx. So I am missing a minus 2 up here, and therefore I need a minus 1/2 out there. So this is really minus 1/2 integral. And I guess since I have to continue with the integral, we better put the bounds back here. Need some space. All right. Now this is going to become dw on top. And on the bottom, it's going to be the square root of u. So this is, instead, we can write that as u to the minus 1/2 power, w to the minus 1/2. That's the same thing as 1 over the square root. And while we're at it, let's go ahead and change the bounds as well for that one. So when x is 0, w will be 1, right? Because it'll be 1 minus 0 squared. And when x is 1, w will be 0. All right. So let's go ahead and evaluate the first part then, I guess. So I'm going to plug in the upper bound. minus the lower bound. And then this integral here. If I integrate w to the minus 1/2, I add 1 to the power, so it becomes w to the 1/2, and I divide by that new power. So I have 1/2 and then divide by 1/2. That's really like multiplying by 2. So these two here are going to cancel. Everybody still with me?
I forgot the x after the cosine in
So am I here?
here. Yeah.
Other than that, you okay?
Yeah.
All right, anyone else have any questions? We good? So 0 times arc cosine, that's 0. And what is the arc cosine of 1? That means what angle does cosine return a value of 1? That also happens to be 0. So that's really nice. All that stuff just goes away. And we are left with minus w to the 1/2 evaluated from 1 to 0. So we plug in 0 first. And then we would have minus a negative 1 to the 1/2. So again, 0 and minus the negative is 1.
Why wouldn't we substitute what w equals back into doing this? Like, why wouldn't we substitute 1 minus x squared back into it?
The reason I did not do that is because I changed my bounds.
Okay, that makes sense. Thank you.
Mm-hmm. Remember, you can do either. You can either leave the bounds as they are and replace the variable at the end, or you can change the bounds and then just plug the new numbers in.
Okay, thank you.
Mm-hmm. Any other questions about that one? So I believe there are 2 more examples here. So I'm going to do the first one. So this is yet another type of integration by parts. And this is called the iterated integral. And I'm not going to actually go into that yet. I'm going to go ahead and start solving the problem and then see if it makes sense why it might be called that. So notice there are 2 functions. So I can choose a u and a v, or u and a dv. The question is, which one do I choose? So there are, we have that little LIATE, right? Liat, that we came up with yesterday. And that told us which one to choose. So if I follow that, it tells me that the trig function comes first. In this case, however, because it's iterated, which is what I'm going to find out in a few seconds, means this thing is going to just continue on and on and on, then it doesn't actually matter which one of these two I choose. Right? Both of these functions are what we would call cyclical. Right? If I differentiate e to the 2x, I'm going to get 2e to the 2x. If I integrate it, I would get 1/2 e to the 2x. And if I did it again, right, I would get 1/4 e to the 2x. And then 1/8, right? I would just get another 1/2 in front each time. So I get the original function back with a new coefficient. Same thing with the cosine. It's going to be cosine, then minus sine, minus cosine, sine, back to cosine again. So these things just keep going back and forth. And so in this case, it doesn't technically matter. So I'm just going to go ahead and choose u equal the e to the 2x, just so I don't have to deal with a bunch of fractions. And I'm going to let dv equal the cosine. So I just need to calculate du and v. So v is going to be sine. And the derivative of e to the 2x is going to be 2e to the 2x dx. So write out the first step. It is u times v minus the integral of v times du. Okay. So that's one iteration of by parts. Let's try one more. So first off, I'm going to take this 2 and throw it out here. This e to the 2x is still there. Did you have a question? Okay. There we go. All right, so I need to choose yet again a u and a du, or u and a dv, sorry. So I'm going to let u equal e to the 2x again. And dv is going to be the leftovers. So that's going to be sine x dx. Calculate du and v. We've already done du. It's 2e to the 2x dx. What's the integral of sine?
Negative cosine.
Right. All right. So I see that I've maybe not given myself enough room here, so let's scoot this down. Okay. So I've got e to the 2x sine x minus, there's a 2 out there. And this integral is now going to be replaced by u times v. Notice v is negative, so I'm going to pull the negative out in front. And then I have minus, again, v is negative. If I'm subtracting a negative value, I get plus the integral. There is a 2 there. E to the 2x cosine x dx. Okay, so that's just these two terms combined. With a decent amount of rearranging. So does anybody see why this is called iterated yet?
Yeah, you kind of get stuck in a loop.
You just keep going and going and going, right?
Yeah.
So it's funny that you know that I always solve this problem now for students, but in most classes, I always thought that we call this problem like a rite of passage, right? This type of problem usually give to students and watch them just constantly do integration by parts, which is a great practice, but you could literally sit here and do this all day if you don't know the trick. So all of this, remember, is still equal to the original integral that we're trying to solve. Okay. Now notice the original integral and what I just got out of that integration by parts. They're the exact same thing, right? So I'm going to call that integral I, just because I don't feel like writing it a bunch. And it'll clean it up quite a bit. So what do I have then if I rewrite this? Well, I've got e to the 2x sine x. This is going to be plus 2e to the 2x cosine x. And then minus 4i equals I. I just distributed the 2 here, or negative 2. So if I have minus 4i on this side and I move it over there, well, then I have 5i. So I have, and let's go ahead and maybe factor out that e to the 2x. And again, I is the original integral. It's the thing I'm trying to find. So if we solve this problem for I, we get this. So that is called the iterated integral. And it's done by parts. We had to do 2 iterations. Got to be careful of signs for sure. And you come back to the original integral, and once you get that, you just combine the original integrals, and what's left over is your solution. Now, as a technicality, there should be a plus c in here. It's just a little less intuitive as to when to write it, because there's always an integral left behind. So just need to add it at the end. So any questions about that integral? So what I'd like to do is I'm going to give you the 2 that are left over. And I'm going to ask you guys to split into some groups, which I'll just let Zoom pick for us for today. So take a minute here to write these problems down, because I don't think I can leave them displayed and split you all into your groups. And one thing I want to note is that for part B here, right, this was under the iterated integral. And this is not cosine times natural log. A lot of people think that it is. It is the cosine of the natural log, right? That's inside the cosine. All right, so I'm going to split you guys up into groups, and I would like you to take that time. Let's see. It's like if I do 6 groups, it'll be 3 to 4 people. Yeah, that's probably ideal. All right, so I'm going to go ahead and do that. And I want you guys to work on those 2 problems. Let's say maybe about 15 minutes, and I'll be popping in and out of the rooms to see if you guys have some questions.
I think maybe we were supposed to stay in the breakout room.
Yeah, I'm just gonna go back to breakout room.
Okay.
In the world of that sound.
Oh my gosh, so sorry. Someone's doing yard work. Let me mute myself.
So I'm just going over the last 2 problems really quickly. right. So let's see, we've got u times v, then I need v du. So this is z to the fourth over 4, natural log z, 1 to e, minus the integral of z cubed. We literally just did that. So I'm going to pull a 1/4 all the way out in front. Then I'm going to pull out the z to the fourth, and it's going to be natural log z minus 1, just preference. So this is going to be e to the fourth, natural log e minus 1, minus 1 to 2. Yeah, good.
When you did your integral for z to the cubed over 4, did you divide by another 4? Because it looks like, because you add 1 divide, but you already had a 4 underneath, so wouldn't that be
How about that?
Yeah, I was just making sure that I didn't do something wrong.
I don't know how you didn't see that the first time. It's clearly written that way. All right. What can we do here? So log of 1, that's 0. Log of e, that's 1. 1 minus a fourth is going to be 3/4. So this is 1/4 times 3 to the fourth over 4 plus a fourth, which means I can pull out another 1/4, make it 1/16. 3e to the fourth plus 1. And the second one here, you would let u equal cosine log. Derivative of that is going to be minus sine log over x. Right, derivative of cosine is minus sine. Derivative of the inside is 1 over x. dv is just dx in this case. So x cosine log x minus integral x times negative sine log x over x. Cancel those. So then you leave this first guy alone. And you'd have technically plus the integral of sine log x dx. You have to do it again. So let u equal sine log. Derivative of that. This is now plus because we had minus a negative. And it would be u times v minus the integral of v du. Again, these cancel. And again, this guy right here is the original integral, and all of this is equal to the original integral. Remember, this is one of the iterated ones. So you have a negative I on this side. If you move it to the other side, you get 2i. And on the right-hand side, we have x times the quantity cosine log plus sine log. So just divide by 2. And you're done. So I know I did that quickly, but you guys were working on the problems, so it shouldn't have been completely new to you. Any questions about those two problems or anything about integration by parts before I move on?
There should be a plus C on the second question for the answer.
Hannah, can't see that? Come on now. You know how I know when I'm teaching you well? When you pick out all my little mistakes that I make?
Yeah.
All right.
We know you put
Anything
them
else?
on purpose, so we find them.
I'm sorry, say that again.
I said we know you put the mistakes in there on purpose, so we can find them.
Sure. All right, I think that's all the problems for that packet. Okay. So let me go ahead and pull up the next one.
I have a question while you're doing that. For the optional homework assignments, no, not for that. Do you have the solutions for those, or should we just look those up?
I do have the solutions, but so someone asked me the other day if I had them, and if I did, can I post them? And I said, sure, except I will not post them until after you've done the quiz on that material.
Okay.
Otherwise, you would just have the solution at home already and just
Right.
regurgitate it on a piece of paper with your handwriting and send it to me.
Yeah, sorry, I forgot that you use those problems for the quizzes. Okay, that makes sense though, and that's fine. That works.
All right. Get that cat under control, whoever that was.
That was my child and his papa.
Oh, sorry. It sounded like a cat.
Yelling, yeah, sorry.
All right. So far we have done U substitution and we've done integration by parts. The next technique that we'll learn is trig integrals. And I'm sure half of you just shut down when I said trig. But these problems are not terrible. There's just a couple set of rules we have to follow. So for sines and cosines, we're going to need these two sets of formulas that are given here on these last two bullets. We need the Pythagorean identity, which just says that sine squared plus cosine squared equals 1. And it's just rearranged here to solve for sine squared and for cosine squared. And the third bullet says we also have these formulas called the power reducing formulas. And that states that if I have a sine squared, I can turn it into a cosine of 2x using that formula. And cosine squared does the same thing. The nice thing is that they're the same formula, just with an alternate sign, right? So the cosine has a plus, the sine squared one has a negative. So our goal is to break off some of these sines and cosines because we're going to actually be using U substitution here. We're going to let U equal either sine or cosine, which means we have to have at least one sine or cosine that we break off. So notice the first bullet here says breaking all factors to evaluate. So that's what that's saying. And it says best to get a single power of one trig function and use a substitution. So that one single power is the one that we will use for our du. So let me demonstrate here with the first problem. it says cosine of 25x times sine cubed all dx. Now you can choose to let u equal 1 or the other, but there is one that is a much better choice. Any idea what that might be in this
Sine.
case?
Sine.
To let u equal sine or to let something else? What are you saying?
I would say to let sine equal u. No. Cosine would equal u.
So I'm assuming you said sine because you didn't want to introduce a negative. Is that right?
Yeah.
Which is a good thought. But because the cosine has the higher power, we're going to let it equal u.
Okay.
So I'm going to say let u equal cosine of x. So du is going to be minus the sine. Okay. So if that's the case, then I need to rewrite this equation. I need to break off one of the signs, and I'm going to slap it back here at the end of the problem with the dx, because that's where I need it. Left behind is going to be a sine squared out front, and then also a cosine to the 25th. Now I also know that if I let u equal cosine, du is negative sine. So I'm going to go ahead and put that in as well, and just put a set of parentheses around those. And if I put a negative on the inside, I have to counteract it on the outside. So I need a negative out there. So cosine to the 25th, that's just going to be u to the 25th. My negative sine x dx, that's all du, right? So this is du. This is u to the 25th. What do I do with sine squared? Well, I said that we would use these two sets of formulas that are given here. So in this case, we're going to want to use the Pythagorean identity that states that sine squared is equal to 1 minus cosine squared. So if I replace it, my problem now looks like this. Everybody good with that?
Is there a reason why you're keeping it in the parentheses, the du, rather than just writing the du?
Personally, I don't like mixing x's with u's.
Okay.
I'm leaving it all as x, and then I'm going to
Okay.
take it and turn it all into u.
Okay, gotcha.
Why is there a negative out in front?
Because for du, we needed a negative sign. So I placed the negative inside. And just like before, when we multiplied by like 3, we had to put a 1/3. This is like multiplying by negative
Oh.
1.
Okay. Yeah. Thank you.
Mm-hmm. So now I've got, if I change this all to u, this is 1 minus u squared times u to the 25th times du. And we can continue from there. So this is going to be minus u to the 25th minus u to the 27th. And if we wanted, we could even take that negative back inside And make it u to the 27th minus u to the 25th. And integrating, you just add 1 to the power and divide by that number. And then the very last step, just like we did with u substitution the first time, is replace u. So any questions about that guy? All right. So the next one here is sine squared. So the question is, what do I do in that case? I'm just checking to see what other problems we have left here. So we have two options there, right? If we go back to the top of the packet, we have that sine squared could equal 1/2 1 minus cosine 2x. And we've also got that Pythagorean identity that sine squared equals 1 minus cosine squared. So out of curiosity, what would you guys choose to replace sine squared with? The power reducing formula or the Pythagorean?
I would do power reducing.
Okay. Any other people want to chime in?
Pythagorean.
All right. Somebody want to break the tie here?
I think Pythagorean as well.
Okay. So if we were to, or go ahead. Or maybe not. Did you want to choose one, Brennan? Maybe your mic's not working. So if I were to use the Pythagorean, how would you go about solving that integral? You'd have to use something for the cosine squared, right? So basically, you've turned a single integral into two separate integrals, right? Because this would be this minus this one. And you still are kind of stuck at the same point that you were before. So in this case, that is not a good choice. Instead, we want to use the power reducing. So that's 1/2 1 minus cosine 2x dx. So again, this is really two integrals. It's the integral of dx minus the integral of cosine 2x dx. But this time, there's not any guessing on how to solve that second integral. That second integral is a basic u substitution problem. So I'll do it this time, but then any other time that we see that recur, I will go ahead and just give the solution. So we would let u equal 2x, du would be 2dx. So I would need to introduce a 2 in here, and therefore a 1/2 out front. So this integral would be cosine u du, and the integral of cosine is going to give us sine. Then replace u. And so we can see that the solution to the integral of cosine 2x is what we would expect for the integral of a cosine. We get back sine with the interior function still the same, 2x. And then the coefficient on that x comes out as a fractional coefficient. So if there's a 2 inside, it comes out as a 1/2. If it was integral of cosine of 7x, it would become 1/7 sine 2x. And then, of course, the integral of dx is just x. So putting it all together, we have 1/2 x minus, now there's already a 1/2 there. And I guess I forgot to bring him down here. Let's see, hold on. We'll need 2 minuses. There we go. Right, there was already a negative 1/2 in front. And oh, that's what I did. Let me just take the negative away. There we go. Okay, so there was already a negative 1/2 in front, and then the integral itself is going to be that, right? Because we had that 2 that I had to introduce, right? So that's where this 1/2 came from out here. So this is x over 2, 1/4 sine 2x plus a constant. All right, so this one we used Pythagorean. This one we used the power reducing. Let's see, which one of these do I want to do?
I had a question on that last problem.
Yeah, good.
Why is it still minus 1/2? Because wouldn't it be positive after you take the integral of cosine? Oh wait, never mind. Never mind. I was confused. It's all good.
It's all right. I think I'm going to go ahead and do sine to the 4th for you. And if we have time, I'll let you guys try sine cubed. So again, I have no cosines present in the problem currently. right? I only have sines. Which one of the two relationships do you think we should start with? Should we use the Pythagorean or the power reducing? Are we afraid to be wrong?
Power reducing?
So I think, again, power reducing is a good choice. But if I try to use the Pythagorean, once again, we would get a cosine to the fourth term. So we'd really just be compounding the problem. So I'm going to rewrite this first as sine squared squared. That's the same thing as sine to the fourth. That way I can replace the sine squared with 1/2. Use a different bracket here. 1 minus cosine 2x. Right, so all I did so far was replace sine squared with its identity. But then I need to square that out. So that's 1/4, right, for the 1/2 squared. Then I have 1 squared. Squaring the binomial, you take the sign in the middle, multiply 1 by cosine 2x. That's cosine 2x. And you would get 2 of those, right? So it's always 2 times the a term times the b term. And if you don't like the shortcut, then feel free to write out 1 minus cosine 2x times 1 minus cosine 2x and FOIL it. And then lastly, we need to square the final term. So that's always going to be plus, and that's going to be cosine squared 2x. Is everyone with me so far?
Yes.
Okay. So now I could technically break this into 3 separate integrals. The only one that's really going to give me any trouble is this guy. All right, we just got done doing the integral of cosine 2x. That's not hard. But this cosine squared 2x looks a little strange. Anyone have any ideas of how we can manipulate that? Any suggestions?
Use U sub for 2x.
We could do that, but I think the real problem is the fact that it's a squared cosine. Right, pretty much all these integrals are higher powers of sines and cosines, and we're trying to figure out how do we solve those.
Could you introduce another power reducing for the cosine squared x?
I think another power reduction might be a good idea here. So we know that cosine squared of x is equal to 1/2. Just move the picture here. 1/2 1 plus cosine 2x. So what if I replace the x in there with 2x? Well, now it's going to be 1/2 1 plus cosine 4x. Right, because I replaced x with the quantity 2x, And if it was multiplied by 2 in this one, well, we just need to multiply this by 2 to get 4x in there. So we can replace cosine squared 2x by that term. And I'm going to go ahead and multiply that. So that's going to be 1/2 plus 1/2 cosine 4x all dx. And the reason I did that is because I want to combine 1.5 and not have to do those as separate integrals. Okay. So now I need to go ahead and follow through with all the integration. So the integral of 3/2 is just going to be 3/2 x. Then we have -2. Now the integral of cosine 2x, we know the integral of cosine is sine. We leave the inside alone. And because the inside has a coefficient of 2, that means when we integrate, we get a 1/2 in front, which we demonstrated above with that u substitution. Then this one has a 1/2 in front already. Again, the cosine comes, or integration of cosine turns into sine. And what will be my coefficient for that one?
1/4.
Right. So just as a quick aside, notice I wrote plus c inside the brackets. It doesn't matter if you put it in or outside really, because you'd multiply it by 1/4, and 1/4 times a constant's a new constant. So you could just call it C1 at that point. All right, do we have bounds at this problem? No, okay. So we can just leave it this way. Let's try to clean it up some. Let's see. Instead of canceling these, I think I'm going to go ahead and, never mind. Let's go ahead and do that. First, I was thinking about pulling out a 1/2 out of everything, but this guy's going to still have a fractional coefficient, so it's not going to really matter too much. That there is your solution. So give me some feedback. Good, bad, no clue. You're gonna cry yourself to sleep after this.
I think I just need to practice doing it.
Okay.
Yeah, I just struggle with like setting up the problem, so like knowing which like identity to substitute in, but I think that comes with practice.
Yeah, a lot of times I think the best way to learn the technique, or to understand which one to choose, is just trial and error. You know, sit down, plug one in. If it looks like it's not going anywhere, try the other. So I believe for sine cubed, I'm going to let you guys try that one, but just out of curiosity, what technique or which one of the two substitutions do you think you'd end up using? So can you look at this problem and make a guess?
Pythagorean.
So yeah, I think in that case, the Pythagorean one's going to work.
Agreed.
Because notice it's an odd power.
Yeah.
So we can break off one of the signs and use that as our du. All right. I think I'm going to come back to this one if we have time, because there's only one example. And let me just make this quick note of this problem. I only do one of these because I suggest not using this technique for the other problems. So notice that this says integrals involving multiple angle integrands. So we have sine of 2x and another one that has a 3x inside. So what I suggest not doing is when doing the problems above is getting any combination of sines and cosines that have different arguments, right? So we, again, 2x versus 3x. And the reason for that is because you have to use one of these three formulas as a substitution. And these three formulas are not easily memorized. They're not something that you just kind of remember from trig, right? So, like I said, let me come back to that one. I'd rather work with tangents and secants and make sure you get a hold of those first, and then we can go back and do that other one. So all the problems I did so far were sines and cosines. But obviously we all know that those are not the only trig functions that we encounter. So the other options that we have, or we see quite often, are secants and tangents. The Pythagorean identities are given there. And I always forget to save this darn thing after I change it. These should not have dx's. What's this? Don't need that right now. So let me get rid of these. There we go. Okay. So we should know that the derivative of tangent is secant squared, and the derivative of secant is secant tan. So with the problems above, right, with the sines and cosines, we would typically break off a sine or a cosine, right? One of whatever trig function we can. In these problems, we need to break off either a secant squared or a secant tan, because we're going to use those as our du. So again, let me demonstrate with this one. So I've got secant cubed, tan cubed. And as I said, we could break off either a secant squared or a secant tan. So I'm actually going to do this the wrong way to show you why it's a good choice to do it the other way. So I'm going to go ahead and say, okay, I'm going to break off a secant squared. So I have a secant left, a tan cubed, and a secant squared. Now, when I make the decision on what to break off, that means I've already also made the decision as to what u must be. Because for du to be secant squared, u had to have been tangent, because the derivative of tangent is secant squared. So if I've made that decision, well, right here I've got u cubed And right here, I've got du. But I've got this other secant hanging around. What am I supposed to do with that guy? Well, the only other tool that I have at hand is the Pythagorean identities, and they require a squared trig function. So there is no simple way to take a secant and turn it into a tangent. So that's what I mean by maybe doing some trial and error, right? I could set this up and go, okay, I have no idea how to get rid of that other secant, so let me try the other option. So let's do that. Let's break off a secant tangent instead. So I'm taking one secant and one tangent and placing it at the end. That leaves me with a secant squared and a tan squared. So that means that in order to get a du of secant tangent, then my u must have been secant. So again, secant tan dx, that's all du. Secant squared, well, that's just u squared. Well, I've also got this tan squared lying around. However, going back up here, tan squared can be rewritten as secant squared minus 1. So I can come back to this problem, and I can replace my tan squared with secant squared minus 1. And so I'm here now. And by the substitutions, this is u squared, that's u squared, that's all du. Any questions about those substitutions or anything that I've done so far? So this would be u to the 4th minus u squared. Integrating those, you just get u to the 5th over 5, u cubed over 3, plus a constant. And the very last thing is to replace u. So we let secant equal u. So our final answer is secant to the 5th over 5 minus secant cubed over 3 plus a constant. So again, let me see how many more problems there are. I think there's 3 more, if I remember correctly. Yeah. All right. I think I'll leave that one for you guys. I think I might do one more here. And then what I will do is I'll do another breakout session. I'll let you guys work problems. At that point, it's up to you if you want to stick around, really. I hope that you do, but you don't have to. But I'll give you that opportunity to work problems with your classmates and ask questions. Let's see. I'm trying to remember which one of these was uglier when it all played out. I guess let me try this tan to the 5th one here. So again, For secant tangents, we require that we have a secant squared or a secant tan that we can break off into du. I don't see any secants in this problem, right? So somehow we've got to get some secants in here. So the question is, how do we do that? Well, the only other thing we were given were those Pythagorean identities, right? So I'm thinking the best course of action here is to break off a single tangent. And the reason for that is that that tan to the fourth is really the same thing as tan squared squared, which means I can use the Pythagorean identity and replace it. Now I'm not at the point where I can make a u substitution yet, because that secant squared is buried inside of a binomial squared. So instead, I think I'm going to be forced to square this all out first. All right. Then I'm going to go ahead and break this into 3 separate integrals and treat each one. All right, so all I did at that step was just distribute this tangent to all 3. All right, so let's look at this first one. I've got secant to the fourth tan. Again, we need a secant squared to be broken off or a secant tan. I think for that one, I'm going to go ahead and break off a secant tan. It could be done either way. Wait, we've already got one tan there. If I just take one secant off, then u is secant, and the derivative of secant is secant tan. So that integral becomes u cubed du, and that's really nice. The second one, I'm going to let, and this time let me use a different variable since I used u on the last one, and they're not the same. Let's just say a is tangent. Well, the derivative of tangent is secant squared. So that one's really nice. That one's just going to give me a dA for the integral. All right, so far I've got integral of u cubed du minus 2 integral a dA. this one, not so fun. So I'm going to tell you that this is equal to, let's see, I think it's natural log secant x. So let's check that really quick. So a quick way you can do this one is rewrite it as sine over cosine and do another substitution. So let's let b equal cosine. We know the derivative of that is minus sine. We would put a negative here and one on the outside as well. So that integral would be minus integral dB over B. All right, so what are all these integrals equal to? Well, this is u to the 4th over 4 minus 2a squared over 2. And dB over B is going to be natural log absolute B. Right, so we've got a lot of variables running around, but that's all right. We defined all of them. U is equal to secant. A is equal to tangent. B is equal to cosine. So remember I said at the beginning that this integral up here was going to equal natural log of secant. Remember a rule of cosine, say if I take this minus sign right here, I can pull it up as a power on the inside. What is cosine of x to the -1 power?
Secant.
It's equal to secant, right? All right, so any questions about that problem? I know there's a lot to that one. I went through it fairly quickly. Any questions? Come on, why are you moving with the screen? All right, so I think there were 3 problems I left behind, minus this guy. But I'm not super concerned about that one. Would you like me to do this one really quick? Or just forget about it altogether?
We can set it up.
All right, so it's got 2 signs in there, right? Well, there's the formula with 2 signs in it. So it'd be 1/2 cosine of a minus b. So I'll call this one a and this one b. So 2x minus 3x, that's negative x. And then it's minus cosine of a plus b, that would be 5x. An important thing to note with this problem is cosine of negative x is the same thing as cosine of x, because cosine is an even function. Otherwise, you have to do a u substitution for that integral. And again, if you just called the first one b and the second one a, you wouldn't have had that problem, right? So there are some little things that you got to be a little clever about sometimes to make your life a little easier. And those are two pretty quick integrals. Integral cosine is sine, and integral of cosine of 5x is going to bring a 1/5 in front. So you get that. So again, this isn't hard. It's just a matter of, you know, how often are you going to remember those formulas? So just as a suggestion, unless somewhere down the line you see ones that have different arguments, do not get yourself in that situation. So back up here with these problems, you don't want to get a combination of something like, let's see, I guess I didn't do any of it here, which is good, but you don't want to end up with anything like a sine of x and a cosine 2x, say, for this problem. So let's see. You've got problem C here for sines and cosines. So sine cubed. And then there's, let's just try this one for now. Tan 10 secant to the 4th. So I want you guys to try those two in your groups. So I'm going to go ahead and break you up again. Before I do that, I will give you your quiz. I'll post it right after class, and you'll have until class time tomorrow to turn that in. So plenty of time, at least compared to the class time that we take to do it. You may collaborate with someone else if you like, outside of class. And we may start doing where I'll have you actually turn in a joint quiz. We'll see how that goes.
Is this for the parts and the trigonomic integrals? Like the quiz is both?
I will probably give you two quizzes, yes. One on integration by parts and one on trig integrals.
Both due by class tomorrow?
Yes.
Okay.
But again, they're only one problem each.
That's great, thanks.
Mm-hmm. All right, so let's see. It looks like, why is there one person in a room? Let me go back to this. I guess we lost quite a bit of people. They got tired. All right, recreate rooms. There we go. All right, so I'm going to go ahead and put you guys in the room. 15 minutes, try those two problems. I'll be popping in and out, ask questions. If you have anything else you want to ask me, let me know.